Welcome back to Integral Calculus. In this video, we're going to be looking at integrals involving sines and cosines. The title makes it sound a little bit odd for this point in the semester. We're looking at sines and cosines now. We've done integrals involving sines and cosines since before this course started. We're going to look at things a little bit more complicated than what you might expect. And I'm going to be perfectly honest, we're going to look at things that are a little bit more complicated than anything that might show up naturally in a model of a situation. Looking ahead in the not too distant future, we're going to learn how to take expressions that don't look like they have trigonometry whatsoever and rewrite them so that trigonometry magically appears. And when we do that, sometimes we're going to end up with some really weird trigonometric functions going on, and trigonometric functions raised to really weird powers. So this is a stepping stone to getting to that point. I have never in my life seen a practical application where sine raised to the 7th power was actually useful, but that's exactly what I want to look at in my first example. The integral of cosine of x times sine raised to the 7th power of x dx. I think that for most of you looking at this expression, your first instinct would be to let u equal sine of x and just see what happens. Well, in this case, du would be cosine of x dx. And hey, there's cosine of x dx right there. This integral simply becomes u to the 7th du. The integral there will be 1/8 u to the 8th plus our constant of integration, and then substituting back in, this is going to be 1/8 times sine to the 8th power of x plus arbitrary constant of integration. All right, that's exciting, I guess. That's one word for it. Let's take a look at another example. Integral sine cubed of x cosine to the 4th of x dx. It's a little bit less apparent here. I want to either let u equal sine or let u equal cosine. It's definitely going to be one of those things. And it's not immediately clear which one it's going to be. So here is your rule of thumb. Because I have an odd power on sine, I'm going to go ahead and work with u being cosine. If I had an odd power on cosine, I would go ahead and work with u being sine. If I had an odd power on both, it actually wouldn't matter. But before I can actually do my substitution, I'm going to have to use a trick using trigonometric identities. Specifically, I'm going to use the Pythagorean identity. I'm going to rewrite sine cubed as sine of x times sine squared of x, so that I can rewrite that sine squared as 1 minus cosine squared x. Right, that's just the Pythagorean identity. Sine squared plus cosine squared is equal to 1, so sine squared is 1 minus cosine squared. Distributing from here, I can take my sine x times 1 times cosine to the fourth. I can take my sine x times minus cosine squared times cosine to the fourth, and I can split that up and get two separate integrals. Both of these integrals look a lot more like that first one that we evaluated. And so the process is going to be much the same. As I suggested before, I'm going to let u equal the cosine of x, which means that du is going to be the negative of sine x dx, and I'll use the same substitution in both integrals. So I'm going to end up with the negative of the integral of u to the fourth du, and then the negative of minus is plus the integral of u to the sixth du. And so we end up with minus 1/5 cosine to the fifth of x plus 1/7 cosine to the seventh of x plus an arbitrary constant of integration. All right. That's not too bad, I hope you'll agree. Although that does leave us with a bit of a question. If you look back at what I did, the end goal here, the thing that made this whole process work, why isn't my scrolling working? There we go. That's something resembling scrolling working. I was very happy to have that odd exponent on sine because it let me leave an extra factor of sine behind that I used in my u substitution. Right? I needed sine x along with the dx so that I could do this substitution at all. Well, what if I don't have an odd power? What if everything is even? And I'll take a look at the simplest case of that. What if we don't have sine at all? What if we just have cosine? Well, there's a formula that you, I'm sure, learned when you studied trigonometry, and I'm also sure you have completely forgotten between now and then. The property we need is called the power-reducing formula. But I'm going to take a step backwards to one that you more likely remember, even if you don't remember the specifics, which is the angle addition formula. Specifically, the angle addition formula for cosine, which tells us that the cosine of u plus v is equal to cosine u cosine v minus sine u sine v. From that angle addition formula, you can then generate what's called the double angle formula. And the double angle formula is just what happens if u and v are the same angle. Then I have cosine of 2u equals cosine u times cosine u, which would be cosine squared u, and sine u times sine u, which would be sine squared u. Now from there, I'm going to use the Pythagorean identity to rewrite this. Cosine 2u will just stay alone for now. Cosine squared u will stay alone for now. And then sine squared u. We just used this in the last example. sine squared is the same thing as 1 minus cosine squared. And you can rearrange this equation to get 1 plus the cosine of 2u all over 2 is equal to the cosine squared of u. All right, this is the power-reducing formula for cosine. I could have, instead of rearranging and replacing sine squared with the Pythagorean identity, had replaced cosine squared with the Pythagorean identity, and I would have ended up with the power-reducing formula for sine, which tells us that the sine squared of u is 1 minus the cosine of 2u all over 2. Those two formulas are absolutely necessary for the process of integrating expressions involving trig functions when all you have is even powers. All right, so let's take a look again at cosine to the 6th power. 6th power is definitely an even power, and we don't have anything raised to an odd power. So I'm going to rewrite this as cosine squared x, the whole thing cubed. Right? Power to a power rule. The cube of the square of x, or the cube of the square of a function, is that function raised to the 6th power. I haven't changed anything. I've just rewritten this in a more pleasant form. Then from here, I will use the power-reducing formula. The integral stays the same, the big parentheses stay the same. Cosine squared x is now 1 plus cosine of 2x all over 2. It's all still being cubed, and we're still integrating with respect to x. At this point, I do need to multiply this whole thing out. And in order to do that, I'm going to remind myself of binomial theorem. You may have seen this at some point in the past referred to as Pascal's triangle. And it's an easy way of raising something to a power. You start off with 1, and then 1, 1. And now from here, when there is nothing above on one side, you just write the 1 that's on the other side. But in the middle, where you have numbers above in both directions, you add them together. 1 plus 1 is 2. Then you have 1, 3, 3, 1. Right? 1 plus 2 is 3. 2 plus 1 is 3. And I'll go one more line. 1, 4, 6, 4, 1. Again, 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. That's how you get these numbers, and it keeps going. Then you pretend that you're a computer scientist, and you start numbering at 0. Computer scientists don't understand. The rest of the world starts numbering things at 1, but that's okay. Nobody's perfect except mathematicians. So raising anything to the 0 power, you just get 1. Raising something to the 1st power, you get that thing. So if you had, right, u plus v to the 1st power, you get 1u plus 1v. To the 2nd power, u plus v to the 2nd power would be 1u squared plus 2uv plus 1v squared. And no, we usually don't write those 1s. but it's just this pattern of following those values from Pascal's triangle as my coefficients. U plus v cubed is u cubed plus 3u squared v plus 3uv squared plus v cubed. And I might run out of room for the next line, so I'll come way over here. U plus v to the fourth power would be u to the fourth plus 4u cubed v plus 6u squared v squared plus 4uv cubed plus v to the fourth, and so on and so on. We only needed cubed in this particular example, so I'll get that last one out of the way so I have room to continue working. The denominator 2 raised to the third power is going to give me 1/8. I can bring that out in front of the integral. It'll make life a little bit easier. And I will have 1 cubed, which is 1. I will have 3 times 1 squared times cosine of 2x. I will have 3 times 1 times cosine squared of 2x. And then I will have cosine cubed of 2x. No, you didn't need Pascal's triangle in order to do this. You could have just multiplied it out by hand. It absolutely would have worked and absolutely would have gotten you the same result. But it was a nice opportunity for me to bring up that as a trick. What is going on over there? I don't know. Apparently, the more I lean over this way, the less that is a thing. Okay, whatever. Yeah. Anyway, the trick works no matter what power you're working with. We're using the third power here, which is just on the verge of not too bad. But imagine you had the 12th power instead. Maybe not here, but up here, you had cosine to the 12th. Then you would do the same trick, and it would be cosine squared to the 6th. So it would be 1 plus cosine of 2x all over 2 raised to the 6th power, and you'd have to multiply all that out. A trick like Pascal's triangle saves you a lot of time and effort and can really make that process worthwhile, a little bit more straightforward, a little bit more doable. All right, let's get rid of that monster that's trying to attack me from the side of the board and continue onward from here. All right, I will split these integrals up. I've got 1/8 the integral dx. I've got 3/8 the integral of cosine of 2x dx. I've got 3/8 the integral cosine squared 2x dx. And I've got 1/8 the integral cosine cubed 2x dx. Some of these are very straightforward. The first two, in particular, incredibly straightforward. The last one, not too bad, using the tricks we've just talked about in this video. The third one, that's the annoying one. Again, it's doable using the tricks that we just were talking about, but it's the one that I really wish I didn't have to do. All right, integral dx is just x. Integral of cosine of 2x. That factor of 2 makes things annoying. You're going to end up with 1/2 times sine of 2x. And then that 1/2 times 3/8 is going to be 3/16 times the sine of 2x. The third integral, we have cosine raised to an even power. So we're going to use the power reducing formula to simplify it. Again, luckily it's only the second power. So it's going to be 1 plus the cosine of 2 times 2x, which is 4x, all over 2. And then I have the third power. I'm going to break that up as the cosine of 2x times the cosine squared of 2x. And let's see what happened now. That third integral I can split up over the addition. I'm going to have 3/16 times the integral of dx, and I'm going to have 3/16 the integral of cosine to the, no, not cosine to the fourth, cosine of 4x dx. And then in this last one, I'm going to need to rewrite my cosine in terms of sine. So I'm going to have 1/8 the integral cosine of 2x times 1 minus sine squared of 2x dx. All right. I'm going to switch colors again just so that my lines become a little bit more clearly delineated. My 1/8 x is still 1/8 x. My 3/16 sine of 2x is still 3/16 sine of 2x. 3/16 the integral dx is just 3/16 x. And now I have some like terms here that I can combine in the next step. Then I've got 3/16 times the integral of cosine of 4x dx. All right, so that's going to give me a 1/4 sine of 4x. Multiply that by the 3/16 that's already there. And all told, that's 3/64 times the sine of 4x. All right, sine 2x, sine 4x, those are not like terms. There's nothing I can do with that. And then what else do we have? We've got, I guess I can split this integral up. Let's close some parentheses over here. I've got 1/8 integral cosine 2x dx. And then I've got minus, I'm not going to have enough room on this line, so let's go down, minus 1/8 the integral cosine 2x sine squared 2x dx. All right. Combine some like terms. I have 1/8 x plus 3/16 x. All told, that's 5/16 x. I've got my 3/16 sine 2x. I've got my 3/64 sine of 4x. And then I've got some things I can deal with. Right? Integral of cosine 2x is 1/2 sine of 2x. We actually have already done that. So all told there, I'm going to have 1/16 sine 2x. And then for my last one here, I'm going to have to do a substitution where u is equal to sine of 2x, which means that du is going to be 2 cosine 2x dx. And from that, I can see that this is going to end up a minus 1/16 the integral u squared du. All right, I've got some more like terms to combine here. I've still got 5/16 x. I've got 3/16 plus 1/16, that's 4/16, or just 1/4. Sine of 2x. I've got 3/64 sine of 4x, and then I will have the integral of u squared is 1/3 u cubed, so it'll be 1 over 48 u cubed. Finally, I've done my last integral, so I can put in my constant of integration. I don't know about you, but I'm tired now. But we were able to get through it, and I suppose that that's what really matters. All right, I'll wrap up with one for you to try. How about the sine squared of 5x dx? Using the tools and processes we've talked about in this video, see what you can do with that, and I'll see you in the next one.